I'm going to speak on the fundamentals of information retrieval, and as much as possible, we are going to illustrate with Apache Lucene library. And I work for Valtech, a Paris-based consultancy company, as a Java developer. So this talk is about the scientific underpinning of information retrieval. That is the core of any AI application. And we are going to go deep into the Boolean and vector space models. That is the principal model used by Apache Lucene library. So we'll see how inverted index are constructed and how documents are scoring. But first thing all, we have to define what is information retrieval. So it is defined as finding material of an unstructured nature that satisfy an information need from within large collections. That definitions is very precise, and many people in IR research consider this as the well defined expression for that. And the material are usually documents, and they are usually text. And you may say, okay, in my language, things are very structured. When we say unstructured nature here, it is comparing to GB application where you have structure in your database. Here, text is free form. And the large collection are usually stored on computers. And one text I like to remember is this from Brain and Page. They say some argue that on the web, users should specify more accurately what they want and add more words to their query. So, and they disagree vehemently to this. And this was in 1998 at the origin of Google when they built their website system. This is to say that an AI applications is not there to give answer to user query, but to user information need. That's the challenge. So the user just tap a query to communicate his information need. It is your responsibility as AI system builder to understand the information need and to respond to the information need, not to the query. When you let's see an example of RR application, you will consider your internal documentation, your corporation. That is technical doc, meeting reports, specification, thousands of documents, and you can assume that a technical people from your staff come and say, okay, I'm looking for a document in Lucene and with cutting because I hear cutting was at the origin, but not Solar because I'm looking at the base base library. And one way to find this is to grab the collection. That is, it's like the grep command in Linux. But this will not be effective. And the question people ask when they build system is to give response in an acceptable time. And also you should be able to respond to flexible query like Lucene and cutting within a slot of 5 words. So another question you have in mind when you build your application, your information retrieval application is at which scale you are operating. Because the scale at which you are operating determines what you are going to do. We have at least 3 scales. The web search, where you search over billions of documents stored on millions of computers. That is why what a company like Google and Microsoft are doing. On the other extreme, you have the personal search. Today, computer operating system integrate information retrieval. You have window instant search, for example. Your email program search is a personal search. And in between, you have the enterprise domain-specific search, where you retrieve, you build retrieval for collections such as research articles, your intranet documents, and outside of a handful of web search company, a developer may encounter these two scenarios, that is personal search and domain-specific search. And that's why in this talk, we are going to focus mainly on these two. So we will consider domain-specific search, and we will look at the models used to implement domain-specific search in the enterprise. The first model, that is the historic one, is the Boolean models. Was the main option until approximately the arrival of the web. And query here is in the form of Boolean expression. We will see this model and we will also outline its drawback. The second model is the vector space models, where user just type free text query, and queries and documents are just viewing as vectors. The goals of the IR application will be to compute the similarity between those vectors. A third model we would like to mention here, but we are not going to explain it more than on this slide, is the probabilistic models. It is a kind of a classification problem where you represent a document and vector in the space, and then you evaluate the probability that a document is relevant to the query. But we are not going to go deep here. We will see that Lucene implements both Boolean and vector space models. So before explaining those models, let's look at some core notions in information retrieval. While you talk to information retrieval people, you will use them like document. That is a unit we have decided to build our retrieval system on. For example, if you decide to build a retrieval system on your intranet documentation, you can say, okay, I represent a document, I take an entire book and represent it as a document. And that will be a bad idea, because if you take a book as the document and you are looking for something like French cuisine, yes, I'm coming from Paris, and we have good cuisine there. You are looking for French cuisine, you can have French in the first page and cuisine in the last page, and that will not make the document really relevant. So the document unit is important. If you take also a sentence as a document, you will miss many documents because them will be very sparse in your representation. So when choosing document, you should take into account precision and trade-off and recall trade-off. And we'll talk later about precision and recall. The second notion is the term. That is the indexes unit. Usually word. Actually, we just say word, but in the information retrieval is not word. It is just called term, and it is the set of terms from your RI dictionary. So if a term is not available in the index, you cannot find it. So you have zero result. The third notion is the index, and the Cambridge Dictionary defines index as an alphabetical list, such as one printed at the back of a book showing which page a subject is found on. So this definition is very good, and you just understand this in our context as that list on which document a term is found on. So you just substitute document to page and term to subject. And we index document to avoid just grabbing the text. You look at the index, you know where the document is, and you just pick the document. The query must be handled quickly at a rate of hundreds to thousands per second, and that is why we are indexing document. This is my reference. They write a very good articles, and I read and read again that article because it's important when you are building search system. So when you build your search system, you should have some measure to evaluate it, and there are particularly two measures. The precision, that is the fraction of retrieved documents that are relevant to user information need. You send 10 results to a user, and he finds that 8 results are relevant. So you have 80% relevancy over the 10 results. That's the precision. And the second measure is the recall. That's the fraction of relevant documents in collection that are retrieved. So you may have 1,000 relevant documents in the collection, but the user is not going to consume those 1,000 results. So you should take a good trade-off between precision and recall. And at Google, they choose precision. That's why they say people are still only willing to look at the first few tens of results. Because of this, as the collection size grows, we need tools that have very high precision. This very high precision is important even at the expense of recall. So you should at least take a decision. And here they take the decision to favor precision over recall. That being said, building search application has 2 steps. First, you build your index, and second, you search over the index. And the decision you take during the indexing step influence the search experience of your user. We will first look at the index structure. If you consider 1 million documents with about 1,000 words, that's nearly 1 trillion words with 500,000 terms among these, which structure will you use? Researchers think about this, and the first answer that came into mind was to build something called term document incidence matrix. That is, you have the term here and the document there, and when a term appears in the document, you just write 1, and if it does not appear, you just write 0. That was the first approach. But they see that this approach was not efficient because there was too many 0 in your matrix. The matrix was extremely sparse, and you really do not want to record the 0. That is why they go into this, the inverted index. And this is that for each term, we must store a list of all documents that contain chi. Identify each by a doc ID, a document serial number. Actually, the library assigns the serial number to each document you add to your index. And this is much more efficient. It's like the index in your book. When you look at the back of the book, you see, okay, this term appears at page 20, and you just go to the page 20. And here, for example, you can say, okay, after AP in this list. In this representation, the set of terms is called the dictionary. And in front of each term you have its postings. That is the technical term. And one entry in this is just called a posting. So a posting is a document ID. And it is important that the posting is being sorted by doc ID. And you will see that it is important for the query to be very efficient. Now, having choosing your index structure, how inverted index is now constructed. The first step is to collect your document. You collect your document, PDF, Excel, Word document, maybe line in your database. You collect this, and then you feed your document into a tokenizer that produces token stream from your text. You extract text from your document, of course. There are good library like Apache just to do that. When your tokenizer finishes its work, the tokens are fed into a linguistic models to remove some superficial differences, and then you obtain your token. Finally, the indexer will take the token and build the inverted index. When the inverted index is built, you are done. So you have your index, and you can now focus on the search part. But we just have two steps: the analysis step, that is the tokenizer and the linguistic preprocessing, and the indexing step. And we are going to say some word about those steps. The tokenizer is given a character sequence. Tokenizer is the task of chopping it up into pieces called tokens. And it is language specific, because in English, for example, you have words separated by space. It's not the case in German. If you are tokenizing German text, you have many words just in one expression. And if you are considering Arabic text, it is even complicated because they are writing from right to left, and you are writing in English from left to right. So the tokenizer is very language specific. And during tokenization, you can drop common terms. It is called stop words, like articles and conjunction. But the strategy is to just first index your document without any stop words. You index without stop word, then you look at the collection frequency, the term that occur in virtually every document are candidate for stop word, because they have less discriminating value according to the query. When you choose your candidate stop list, you let your domain people decide what is important for them and what is not important. Being careful, because if you suppress some word, you may miss some phrase query, like Queen of England. When an user type this, he wants the Queen of England. He needs Elizabeth II. He don't want a queen is visiting England. No. So you should take this into account. Another phase in the analysis phase, another step is the normalization. That is, if you search, for example, for USA, you might hope to also match document containing u.s.a. And The normalization is the process of canonicalizing tokens so that matches occur despite superficial differences. During normalization, you will remove accent and diacritics, something like that. You will capitalize, you will capitalize case folding to lowercase later all your text. And you can also perform stemming and lemmatization, that is reducing inflectional form and sometimes derivational related form of word to the common base form. With porter stemmer, you can have the word brief for the term listed here. But you should be careful because stemming increase recall while harming precision. And you have to choose a trade-off between precision and recall. And in a web search engine, recall is not that important. We see that at Google they choose precision, so they are not going to make any stemming, I guess. So you have to be careful about this. And in my application, in some application I developed, we refrain from using stemming because you lost some control on your term. For example, if you use some famous French stemmer, Java is just stemming to Jav, J-I-V, and you don't know exactly why the A is just dropping. So you should be careful about this. Rather than stemming, going for stemming, we use classification. If we need that, we need to categorize our text. Finally, you have the indexing step. That is a kind of map reduce activity where the map just take the doc collection and produce a list of term ID, doc ID, and the entry with same term ID are merged. That the breaches here will be merged in only one entry, and then the reduced term will take a term ID list of doc ID and produce different posting lists. That is what you can have here. And in practice, you have positional indexes because you need to perform phrase query on those index, and to do that, you need doc frequency. That is the number of documents in which a term of a P. You need term frequency. For example, here ambitious have a doc frequency of 1. That is only one document in containing this term. You need also term frequency and positions to resolve phrase query. Here we have an example that says that Lucene is present in 128 documents, and doc 1 contains 2 occurrences of this term at position 1 and 8. So your index is something like this. So that is the index construction. How Lucene model content, that is the subject of we are going to see now. In Lucene, to index your raw content source, you must first translate it into Lucene document and fields, because Lucene model content as document and fields. Document is what is returned as hit. When user make a search, you return a document, but it's not actually the content holder. It's just a set of field, and field itself is what searches are performing on. It's the actual content holder. For example, if you are indexing some article, the article can have an author field, an abstract field, and then all those fields will be merged in one entity called document. You also have multivaluate field. I wanted to mention this because sometimes people prefer catch-all field than multivaluate field. Multivaluate fields that if your article has multiple authors, you can still add to your document the field with the same name author with the different name for your author, rather than concatenating it somewhere and add to a field as a catch-all. Because when you use multivaluate field, you have more control on your index than with catch-all. And when you index, you have some option. Those options in Lucene is available in this enum, field.index. You have option for indexing. You can decide to analyze the text you are indexing, that is shopping into tokens. It is useful for body and title field. For example, you can decide not to analyze it, so you use the entire field as a token. You can decide to analyze but not storing norm. And when you do this, you decide that you are not going, for example, to boost field. We will see that you can boost document and field to make it more important than others. So you can decide also not to index. And you have also option for storing your field. You store field because you need to give some snippet to the user when a document match its query. And to add a field to a document, you just have this instruction like document.add, you create your field with the name and the different option. It is very simple. You also have option for boosting your document, so you instruct Lucene to consider it more or less important with respect to other document in the index when computing your relevance. So you just say document.set boost. If the value is greater than 1, you upgrade the document. If it's less than 1, you are downgrading the document. And you can do the same for the field in your document. To add a document in your index, you use an index writer. This index writer is actually the class in Lucene that write into the index. Index writer add document, you add the document, and after analyzing the input, Lucene store it in an inverted index. That is token extracted from the input doc are treated as lookup key. And Lucene index directory consists of one or more segments. Each segment is a standalone index, and when you decide to update a document, Lucene just mark the document as deleted and then add it again. And because they use multiple segments and the way they update document make Lucene a dynamic index tools, because Lucene do not need to rebuild the entire index to update a document, and that is very important for efficiency. Okay, that is when you index your document, you can now make search on the document, and to perform your search, you have two models in Lucene. You have Boolean model and vector space model. Let's see at the Boolean model through a first example. Let's look at the execution of an query. For example, I have Lucene and Solar that I'm executing. The software will locate Lucene in the dictionary and retrieve it is posting. We see what postings it will locate Solar and retrieve it is dictionary too. In the dictionary and retrieve it is posting too, and merge the two posting. Merging the two posting is just navigating through the posting simultaneously. That is why document ID are the posting are sorted by doc ID. You just remove the intersection of the posting, and if X and Y are the length of those posting, you will do this in OX plus Y. So it is important that the posting be sorted, but as a developer, you are not concerned with this. Lucene's already implement those structure for you, but it's important to know how it works. So the Boolean retrieval model is being able to ask a question that is a Boolean expression. Boolean query use and, or, and not to join query terms. And it's just view a document as a self-out word. It is precise, document matches condition or not. And Lucene adds some shortcut like plus and minus. Plus is to say, okay, this document, I should have this term in this document, is mandatory. And minus is just to say this term is forbidden, to simplify user query. But this is a view for, is important for expert user. They know exactly what they are looking for. So the Boolean query comes with some problem. That is, often it results in either too few results or too many results. The and give too few and the or give too many. And it is considered for expert usage because you know exactly what you are looking. In one of my projects, the business people say, okay, we are classifying text, we are categorizing text, but if a user sends a query with a Boolean expression, we are not going to go through our classifier. We just execute it as is. He had no result. He's an expert. He knows exactly what he is looking for. And that is how this is sometimes considered. It is also limited with respect to user information, and that is why the model has been extended to account for term proximity. You can actually execute Apache Lucene within a slot of 10 words. So we need to go further than the just Boolean model, and because a Boolean model only records term presence or absence, we wish to give more weight to documents that have a term several times, as opposed to that document that contains it only once. And to do this, we need to record the term frequency in the index. Also, Boolean query just retrieve a set of matching documents, and we wish to have an effective method to order the result. You cannot send just 1,000 results to an user. A machine can process it, but not a user being. And that is why ranked retrieval come into play. So in ranked retrieval, user just send free text query, rather than a query with operators, Boolean operator. You just type words in the natural language. And rather than a set of documents satisfying a query expression, in ranking retrieval, the system return an order over the top document. Sometimes the first page you have the top 10 document. So large results is not an issue anymore. But the premise is that the ranking retrieval algorithm works. So that is where it is very important. And here you are saying to the user, I understand your query, I understand your information in. Those are 10 documental response to your question. So the score is the key component of ranking retrieval models, and in the following you will see how the score is computed. So the first step to computing the score is to look at the term frequency. We see we want to value document containing the term multiple times. So we can just say the simple way is to say the score of the document with respect to the query is the term frequency. But this will imply that a document containing a term 10 times is 10 times more relevant than a document containing it just once, and that is not correct. And so we said because certain terms have little or no discriminating power in determining relevance, we know that is why stop words are sometimes dropping out of the vocabulary because they have no discriminating value. So we need a mechanism for attenuating the effect of frequent stamps, and that mechanism is the inverse document frequency. So the inverse document frequency is defined as the number of documents in the collection, that is n, that is the total number of documents in the collection, over the document frequency, that's the number of documents containing the term t. And the logarithm is used just to dampen the value of the IDF because the function that's in y equal x go too fast. We need to dampen its effect. So we have this for attenuating the effect of frequent stem. And this leads to this weighting scheme called TF-IDF weighting of a term, and the definitions is as follows. Here we have also a logarithm to dampen the effect of the term frequency. And this is not, you have many variations of this. We can use other sublinear expression, and you will see that Lucene use square root as a damping function. So this is a best-known weighting scheme in information retrieval, as not for people using domain-specific search. And it increases with the number of occurrences within a document, and it is this expression, the number of occurrences, and it also increases with the rarity of the term in the collection here. So if you have right terms occurring multiple times in a small number of fields, you will have very good score for that document. So at this point, we may view each document as a vector. You know, a vector, you have many components, and the value of the vector at that component, the value will be the weight, the TF-IDF weight. We just see the expression. And it is an n-dimensional vector conceptually, but in practice, in practice we use q-dimensional vector because it is not important to take every term. It's not important to take every term in the collection because it's the query that is important. We just take term that appear in the query to build our vector space. So when you represent this, you have the vector space model. And in the vector space model, the idea is that the set of documents in the collection are viewed as a set of vectors in the vector space. The axis for each term in the query. User query is treated as a short document and represented also as a vector. And VSM computes the similarity between the query vector and each document vector in the vector space. Then it ranks document in decreasing order of the angle between query and document. So the query and document are represented as is, and then you just look at the angle between the query and the document. But that is not, it is not easy to compute the angle. So instead of ranking in decreasing order of the angle, the VSM will rank document in increasing order of the cosine between Q and G. And that's why you will certainly hear that Lucene use a cosine similarity algorithm. It is just looking at the angle between document and vector in the vector space. So the cosine similarity, the equation is as this. You have the dot product of the vector representing the query and the document that is divided by the Euclidean norm to have a not vector. And this is fundamental in our system based on VSM. If Lucene use this formula, and depending on the library you are using, they will sometimes modify it. Many variations are available. So Lucene combines Boolean model and vector space model. Document approved by Boolean model are scored by VSM. This is a weighted zone scoring or ranked Boolean retrieval. Now you just use Boolean model to compute your document, to select document from the collection, and you use the VSM to restrict the computation of the score to only relevant document from the collection, and you send the most relevant one to the user. So Lucene refines this, and the formula is not sometimes easy to understand, but the idea behind the formula is those. Normalizing document by the Euclidean length of the Euclidean length, remove all information above the length of the document. It is fine if the document is made by a successive duplicate of distinct terms, but if your document is long and contains distinct terms, if you normalize with Euclidean norm, you lose many information. That's why Lucene introduced doc-length norm, and you will see in the formula doc-length norm, it is just a compensation independent of term and document frequency. You also have user. You also know user can boost document at indexing time. So in the scoring algorithm, you should take into account the boost the user decide to affect to a document. At the same time, the same apply for the query, because you can boost the query, and in the formula, in the finite scoring algorithm, you should have you take into account the boost the user affect to the query. So a document may match a multi-term query without containing all the term in that query. And you should favor document containing much of the term in the query. That is also affecting the scoring algorithm in Lucene. So finally, if you assume that a document has only one field, the scoring algorithm is this. You have the cosine similarity. You normalize the query vector, but not the document vector, where you have the doc-length norm, and you have the boost information and the coordination factor. Finally, you can derive from this the definitive algorithm used in Lucene. The default similarity class in Lucene implements this algorithm, where you have the term frequency, and with this sublinear expression to dampen its effect, the term frequency in the query is assumed to be 1. And inverse document frequency is given by this, where you have number of documents over the document frequency of the term. They add +1 to avoid division by 0. The inverse document frequency is squared here because it appears in both query and document. And the query norm is computed by the query weight object. This is the internal object in Lucene that represents the query, the user type. And it is that object that decides which scorer to use, depending on the type of the query. The norm information is this. It is about boost information and length norm. And length norm is computed so that shorter field contribute more to the score. Because if you want it's an implicit way to boost a field in Lucene is to consider it as a shorter field with so many keywords that describe as many keywords as possible that describe your document, and then you will have a very good score for that document. So that is what I prepare as fundamental of information retrieval, and I would like to thank some people before the end of this talk. I use material from this book. It is a good book that contains a mine of information on information retrieval. I also thank Lucene dev team because they make a great job. I went to a client, he want to implement a search engine. He said, okay, maybe it will take 8 months or 1 year. And I say, okay, I can do it for you in less than 1 month. He said, oh, you are a genius. But Lucene team do that for me. It's not me, myself, which implement it. I just use Lucene. And also, this is a great article if you are interested in information retrieval. This article is at the origin of Google today. I also like to thank the authors of Lucene in Action. If you are planning to build your application with Lucene, buy this book. It is very important. In addition to Lucene API documentation, this is very important with many tips. And Apache Con Europe organizer, I thank you. Because of you, we are here today. I also like to thank my company management, which allow me time to prepare this, and my family, Michel, my Daniels. I called my kid this morning, he was crying. He said, okay, good luck, Dad. I say, okay, thank you. I will do as much as I can. I thank my wife too for their love. And of course, I would like to thank all of you for your presence and your attention. Thank you so much. Well, how term frequency is computed? It is from the definition. The term frequency is referred to a document. So you take a document, you say, okay, I'm looking for Lucene in this collection. You take a document, document 1, contain Lucene 10 times. So it is recorded at indexing time that Lucene appear in that document 10 times. And during, at such time, Lucene just look at that information. Because it's not computed at search time, it's computed at indexing time. When the term is added in the inverted index, for each document containing the term, he also records the number of times the term occurs in the document. And because he has the postings, that is the number of documents containing the term, he also records in the index, in the inverted index, how many documents contains the term. And now we see the formula for computing the TF-IDF weight. That is the square root of the term frequency, and that is just calculus, using information in the inverted index. The vector is just, it is conceptual. That is, if your query contains 2 terms, let's say Lucene and Solar, you will have a 2-dimensional vector space. That we will consider only Lucene and Solar as term. And we will look at document containing Lucene and Solar. And the first axis will be Lucene. You will have the value of the Lucene. You know, in this vector space, the coordinate will be, let's say, 1 and 2. You have document G, its coordinate is 1 and 2. It means that it is TF-IDF weight for Lucene is 1. It is TF-IDF weight for Solar is 2. And then you can represent the vector in your 2-dimensional vector space. Yes, when we classify document, actually you have, in Lucene, you have something called payload mechanism. And starting from Lucene, I think 3.2, you have payload token filter, something like that. So we classify and we add the category in our index as a term, but with a boost. We downgrade the boost of the category to favor query matching exactly the term in the index. So we have a model. You call the model, the classification model is independent of Lucene. When you tap when it is to index a document, we just call the classification and say, okay, from which category is this document? The classification algorithm says, yes, this is from class 1 with a probability of 70%. So we take 70% as the boost. We say that is 0.7 as the boost. Because it is less than 1, it will downgrade the value of the category. And then we add that in our index as a payload. And we modify the default we extend the default similarity class to take into account our category payload. That's how we use it, and actually it works. If you tap a query and your term match exactly the term in the dictionary, you will have the high boost. But if you don't match, if you tap e-marketing, you will have e-marketing first, and you also have web marketing second. Okay, I thank you one more again, and I wish you a nice day in Sinsheim. Nice conference at ApacheCon. Thank you so much.